We start with standard images that we turn into depth map. From there, we'll recreate a 3D point cloud from a single point of view, but it's much more interesting to generate entire scene by fusing that multiple point of view with DepthAnything v3. That means also recreating entire 3D Gaussian splatting experience and going into the semantic aspect by labeling imaging and projecting the labeling onto the 3D Gaussian splatting to get semantic Gaussian splatting. Also, we're working the geometry and recreating complex 3D scenes with this model and comparing that to traditional photogrammetry like the racket or the car or any other things. We are really standing at a critical inflection point in spatial computing because we have been relying a lot on traditional sensor-based photogrammetry or LiDAR reconstruction for high fidelity capture. But I'm wondering right now if we cannot get an entire dense geometric and visual reconstruction from a single unconstrained 2D dataset. This really is a redefinition of the 2D to 3D pipeline with inverse graphics. So I'm Florent, my professional focus was always on geomatics and geospatial metrology. So from terrestrial laser scanning reconstruction to a massive photogrammetry project. But one fundamental bottleneck has always been data acquisition. And today, we'll confront that bottleneck by leveraging the cutting-edge large-scale AI foundation model. So where do we start? This will be my innovation engine. As you can see, this is a simple Python script that has several steps. So before that can work, we need several things. First, I gathered data. So what I did is I took my smartphone and I took a bunch of pictures of various elements. So as you can see here, this is the book that I wrote on 3D data science with Python, and I took multiple view. I wanted to have something that is white because this is usually very, very tricky to reconstruct with classical photogrammetry or SFM, and also with some reflection. So this will be one test. Then I took my car. It was really a crappy rainy day, and I took several pictures of my car outside to see also how it handles reflection. And there are a lot of applications that can make use of 3D reconstruction in close to real time so that you can see impact for insurance company also. So this is also something. And as you can see, I have my guitar, a racket that will be also pretty interesting because it's very fine lines. So we may be able to see how we handle that. And after that, my tennis shoe. So this is also cool because for all the prop modeling or yeah, if you're in the shoe business, I think it's very important to be able to reconstruct 3D sets. So that's our starting point, this folder with a lot of pictures. And I intend to do another video where I will actually inject video of complete scene to test this feed-forward capability of what we are going to use. So this is the data setup. Now let's talk about the code setup. So what I'm using, if you want to replicate, essentially is Anaconda or Miniconda. It works with both. I just created an environment called Anything because in it I have Map Anything, I have Segment Anything, Depth Anything. I have various versions from before, and I wanted to see if I can leverage that. So some stuff has evolved, so I could not, and some other could stay static. So to set up the environment, I think the best way to start is to go onto DepthAnything 3 website, recovering the visual space from any view. And in here you have the GitHub repository. So if you are used to using GitHub, you just clone that. And so what I recommend is that you follow the installation that you see here. To avoid most of the issues when installing, I advise to use that first. And if this works perfectly, maybe you can go to that or that. This is really if you want to leverage the 3D Gaussian splatting side of things, which will target GSplat library. And I have to say that I had several issues when I installed everything here with DepthAnything 3. It's a bit more complex to set up than other, let's say, libraries, but still they made a very good effort to make it as easy as possible. But I will not be able to troubleshoot your specific setup. If you have really annoying errors, just drop them below and we'll see what I can do about that. Anyway, so one thing is that they have several models. This is also something that is important to have in mind, is that if you're in a professional scenario, be very careful as to which model you will be using. In here, it's just showcasing the best capabilities, so I will be using the biggest model, but as you can see, this is non-commercial, so Creative Commons. So if you want to use it commercially, you need to downgrade a bit. All right, so installing that means you duplicate that either with Git or you clone it and you download it, and you will see now that in my folder DA3 I have a folder DepthAnything. So this is what I got after like cloning the repository. And then in the source folder, here I put various scripts that I wrote, and the one that I will be using is this one. And under next to it, you have depth_anything_3, and this will be called, the API will be called in my script, and this is what you have normally here, DepthAnything.api. So we take the API module. All right, so that's it. I installed it. I followed the recommendation with pip install all. I had to fix various bugs and make sure that I have all the libraries. And once that was set up, we are good to go, and we can actually explore our DepthAnything. Now we are ready, and we can dive onto this R&D journey. This is fantastic. This is something that I've been wanting to do for a long time, and I'm very happy to bring that to you and show you also my way of thinking around creating this full methodology. So as you can see, I import a bunch of library. What is important to note here is Torch by Torch. Here I'm leveraging heavily my graphic card, which is CUDA compatible. If you don't have CUDA, you'll be very limited. And of course, DepthAnything API. What I do here is really something that I like to do is initialize all my visualization helper so that I can clarify the concept I'm talking about. So here I have two main helper. There is the function that will help us visualize the depth and the confidence map of the prediction. And the second one will be very useful to visualize our point cloud with OpenCV. So I will just execute that, and my three functions, including setup path, are set up. So now we can move on to the follow-up. Right, so we want to load the DepthAnything 3 model. And as you can see, I created a small function, but what is very important to note is that I check if I have CUDA available, and I will retrieve from pre-train. So this using the transformer library from Hugging Face, very, very handy, but you can also retrieve that locally. So let me just execute that, and it may take a bit of time. And as you can see here, I have an issue that I did not solve because it's not so important, but I know that if I want to push performance to the roof, it would be good to have this Triton library, which is actually very nice, that I use in other projects, but in here I had too many issues, so I did not double down on that. So you can see that my DepthAnything 3 model is loaded successfully, and this is my object torch that is there. So we can move on to the next stage, which is the step 2, where we will load the image from a specific folder. So what I do is I check from my extension, and then I will extract frame from videos if we need. And this is what I'm saying. This is something that I want to focus on another video because it brings a whole other dimension that is super cool to explore as well. So here, the theory is that we should be able to load very easily all of our data file. So here, the path that I set up here is Star Wars. So it will load the Star Wars thing, but maybe you can start with the cars. So we'll just put car. And now, normally, if I do that, you see that it found 13 images in the folder. So let's see, data, car, and I have 13 images, which are here. All right. So this looks good. We can move on to doing the inference. So in here, we'll do the inference, but before getting there, I think it would be important for me to explain a bit what's happening and the theory that I'm thinking to test here in this R&D journey. All right, so this is this little app that I coded, and I wanted to use it to show you a bit what is the overall process. So the first thing is that we have this 2D image of our car, right? And what we will do is we will first generate the depth map that you can see here. So this is for each image. And after that, what I do is a pixel projection. So we unproject each pixel based on its depth value. So the flat image is made 3D essentially. And this is only after that that I will showcase the multi-view fusion where we have all the various point of view and we merge that into the 3D dataset, but also showcasing the ability to extract Gaussian splatting. And really something that I've been wanting to explore for a very long time is the labeling process. What about creating a little GUI or so that allows you to label images and then propagate the label onto 3D dataset, but also using multiple images and propagating that as well. So this is the project that I want to build with you here, and we can get back already to our inference because this is what we'll have. As you can see, the depth and confidence will be here extracted. So let me run the inference and we will check here the amount of time needed. Conversion to prediction done, 3 milliseconds. Can you imagine? So it's not a lot of images. If you're used to play with large photogrammetric dataset, this is not a huge one, but you have to imagine that it's really 13 pictures from a smartphone, no calibration at all. This is really totally random with very bad weather and so on, and it's able to have some result. What kind of result? This is what we will see, but still pretty impressive. So in the plot, you can see that I have my image. This is the RGB, this is the depth map, and this is a confidence map. So of course, because of the image structure and how DepthAnything was trained, we see that let's say the confidence is better for objects that are closer or that pops out from the image, but still it looks like we have something pretty relevant. And the more you go far away, the less confidence you have. Okay, so now we have the depth map. What is the next stage? To generate the 3D point cloud from that. And this little function do just that. And at the end, what I do is I will merge the various point clouds. So what I do here is for each image, I generate a depth map. For each depth map, I generate a point cloud. And because DepthAnything v3 is able to get the world coordinates of the images, the interior and exterior intrinsics, it allows us to know the relative position to one another, which means that I don't need at this stage to use any registration mechanism on 3D point cloud, but maybe also one way to improve the quality of the reconstruction. Nevertheless, so let's execute that. As you can see, my full point cloud is around 1 million point, and this is my scene. So very curious to see what it does. Okay, so pretty good, right? You have the car that is reconstructed in 3D. So already here, if you are not at all in the surveying or mapping industry, this is mind-blowing, because if I were tomorrow to put that on a server and make this a complete app, then anyone could take pictures and retrieve a 3D model. That means that if you have a crash with someone else, a little thing, you can just go out, take some pictures or a video, and you will retrieve a 3D element. And the idea would be, okay, I want to tag the part that I really want to be emphasizing on, and either you have a better process there, or you have the follow-up of action there, or this is sent to the insurance company. We can imagine a lot of scenario, but this is fantastic. And also you get the color as well. So I retrieve that, right? It's not direct, but using that, you will retrieve the color as well. So aside from the main element of interest, you have also a bit of contextualization. So you see the bike of pink bike of my wife, some stairs here that goes up, and yeah, the facade is really bad, but you get it as a contextual element, let's say. So super interesting. And also something that we'll be monitoring is it actually accurate metric wise? Because I didn't put any constraint here. As I mentioned, it's not calibrated, it's a smartphone. So what I will do right after is take a tape, measure the car to know it, but we could also match that to a database. That's also a fun experiment, because you can match the car model to a database, retrieve the metric or the dimension, and then you can constrain it fully automatically. Okay, so it works. We have our point cloud, it's combined. So already at this stage, if I were to stop, you have a solution that take any image and return a register point cloud. So this is absolutely stunning. Now, if I visualize it again, let me just visualize it again. It's a bit noisy. So you see it's upside down. This is okay. We can fix that, but not necessary. But it's a bit noisy. You have a lot of point that floats everywhere. So this is optional, but I wrote this additional step that actually will filter out your point cloud. And I wanted to test out two things, because it's often very easy to get stuck onto being able to process only small scale point cloud, but here it's not the case. So what I wanted to explore is, okay, what if we use the Open3D built-in function against something that I wrote, and see how long it takes. And as you can see, if I take the Open3D, it will take 3 seconds to clean, whereas under one second, so almost 2 to 3 times quicker with SciPy. And what do we have here? A point cloud that is much cleaner. So what I do is, it's a heuristic space, so I will compute a large number of let's say, neighbor for each point, and statistically, I will see the distance from one point to the other, and I will put a threshold, and if it's above this threshold, then it gets scrapped out. All right, so this is now our car. Fantastic. Fantastic, fantastic, super, super nice. Now, let's export the Gaussian splatting. So this is also very handy. It uses GSplat, and this is what I will be doing. So I will export my Gaussian splatting by looking at the export format. Here you see that you export, this is built in with DepthAnything 3, which is fantastic. I pass in my image. Okay, I have some issues, but nevertheless, we'll see that later. My image files, if I infer Gaussian splatting, the process resulting method, the output directory that I configured, the thresholds, I think here it's 40%, and the number of maximum point, and if we want to show the camera. And it will export a GLB file. Okay, so this is what I did. So now if I open my folder, DepthAnything 3, if I go into results, I now have car. I have the depth visualization, so let's open that first to see that for each car, you have its corresponding depth. This is fantastic. Now we have the scene, which is here. So a GLTF is super nice. Usually, you know, I like to use Cloud Compare, but in this case, because you save both the points, geometry, and the camera position, it seems not to be able to handle it properly. So you have an error. I'm showing you what you will have if you were to load that. So if I were to load that, you see not any faces, so nothing happened. And I've been thinking, okay, maybe this is also a side quest, but I wanted to bring a solution to that for everyone. So I'm putting up online, you will see just down below the link, the ability for you to visualize GLB file right away in your browser. So let me open it. This is how it looks like. So if you don't have a dataset, you just click on load sample dataset and it will load my tennis shoe that I dragged and drop. But in this case, let's test it live. This is the scene, and I will just drag and drop it, and we have the scene. And as you can see, this is our car with the various camera position. This is fantastic, right? Because to have something like that before, the process was much longer, much more complicated is not the term, but I did some tests on the side to see how long it will take. You have at least a factor 10 to get the same result with a photogrammetric process. However, usually it's much more tighter. But here, remember that there is no registration applied, so it's possible, and this is why it works here, because you have a flat surface. It's also nice because we will be able to have this registration stage as well. Okay. That's for the GLB. For the Gaussian splatting, same thing. And here is the resulting 3D Gaussian splatting from the car dataset. So as you can see, it's pretty darn good, right? You really can do a lot of things with that because it looks pretty stunning. And if I were to, so that you can see, that's the input image, depth, and here is the Gaussian splatting. So pretty happy knowing that it was very, very fast and the training stopped very, very early on. So super, super cool stuff. I have a Gaussian splatting viewer that I'm building, a small one, again, just to loading. And so you have this kind of toolbox. I will not put it under this video. It will be for another video. But what you can see is here, you have the Gaussian splatting. So what we could do is, of course, open it with Cloud Compare. You remember, all the hype about 3D Gaussian splatting is something that if you've been using Point Cloud, you can get ahead from, because it's essentially just a point cloud. The very cool stuff is that now, because you have a lot of additional spherical harmonic as features, it makes it super, super nice, because you clearly see, or at least from my point of view, when I wrote my thesis, it was a smart point clouds. So trying to inject intelligence on the raw data, the point clouds, and work there. And here, this is another step to confirm that this hypothesis, right, when I was doing my PhD, was right all along, that using point cloud, because you can have access to that as well now. So you see that's all the spherical harmonics that are saved there. Not all here, but some of them. So if you want to see the color, just use DC0, DC1, DC2 for now. And this is the Gaussian splatting. So of course, it's mega noisy. So what I will do is just for the experimental side, just go there and have this little tool. Now, what you could do is use the same filtering. So you have one built in with a cloud compare. I will use 20 and just put away really with this technique. And here we go. So this is the resulting stuff. As you can see, this is fantastic. You even have this little curve, right? And this is the Gaussian splatting. If I were to visualize it, I will showcase it afterward. You have something super nice. So now, time for test, which is taking 2 points here. I think I will take things that are easy for me to identify. Yeah. I will take this point here and the end of the door. So this is, I will actually make a follow-up video to showcase the complete workflow that will come in a couple of days. But this is the idea. Here, I created this little interactive masking tool where the idea is that you will label your image. This is normal that you have a difference of color because it's BGR instead of RGB that is loaded. What I did is I created some keys to label, and I have a brush size that I will adjust to 10. And the first class will be the wheel, for example. You see, I put them blue. Then I will make another class, which will be the window. Here one, here one, here one. And the third class, which could be the ground. For example, I will augment the size of the brush to keep the ground here. Okay. Fantastic. And then I will make another class, which could be maybe something very small, which is I don't know how it's called in English. So that will be the idea. You label it. Once you're happy, you save it. And then essentially it will be applying the mask onto the point cloud and looking at what it does. All right, so this is the mask applied to your point cloud where you gather the ground, the wheels, also the windows, and I think I made a mistake, didn't save that. But you see now that you are able to work in the 2D domains and project that on the 3D domain. So that will be for another time. So what is nice is that after export, you see that you have the complete label scene or the Gaussian splatting mask of the point cloud. So let's take the mask, and if I add, normally I rate it in segment label, which means now that if I apply, I take my point cloud, Gaussian splatting, if I go segment label, you see my various labels that we had. This will be for the next stage. So what I want to show is the result here and explore a bit in depth the result of the various data set that we have. So if you remember from the beginning in data folder, we have all of that. So let's work a bit with it. I will just move up. I will not rerun everything, but essentially what I will do is I will change my path setup here and move with that. So the path will be, then let's try the book. So if I were to do the book, okay, then I run the inference, you see, with the confidence map, and then the point cloud, without filtering it. I will not export, but this is to see what kind of result we could have. All right, so here, this is what I was thinking. We have some misalignment. You can see that with the table. It's white, it's a bit complex, but still, you get the shape, essentially, and you also have, you can almost read the preface of Dr. Ulf Baker. Which is super nice, and a bit of the stuff that I wrote on the board, it's not entirely good. So this is for the book. What else did we have? The guitar, if you want to see. I guess the guitar will be complex. So where was it? Here. Guitar. Let's run it. Let's run the inference. And this is also good because you can see how quick it is, 2 milliseconds. This is insane. This is really insane. I mean, that comes from also working since more than 15 years with AI and developing a lot of very cutting-edge AI with 3D deep learning and such. But here, what you can do with a foundation model now, imagine this is just a massive files with weights and biases and a bunch of numbers and a bunch of characters, and you get that from it. So the guitar is, Is it usable? So it's nice because you have the scene, the guitar. Yes, you have one misaligned. That would be maybe better off if we were to redo it, constraining it a bit. So the guitar is not entirely good. Let's see the shoe. I think this would be super cool. The shoe and the Inference. This is good because it's there is a high contrast, so you see that there is a high confidence on point cloud itself. Yeah, this is the shoe. What we will have. It's pretty good, right? There is still some misalignment, some deformation, but we have also a bit of reconstruction inside, which would be hard to do. So yeah, this is very interesting. So here is the shoe results. With the car, I need to go through the process that I'm showing in the 3D Reconstructor course to clean, because else you cannot explore it in here. But this will be for another time. For the shoe, this is what the Gaussian splatting look like more or less, right? So pretty nice. Could be better, but remember again, this took me around 10 seconds to set up, put the shoe on the ground with nice light, just did a round of 10 pictures, and that's what we get in 5 milliseconds. So I think this is already a massive improvement. It's hard to beat performance-wise, but also quality-wise, it's getting serious. And here is the racket, as you can see, pretty good, but what about the actual, yeah, I think from a single you could have, but multiple, I think it's a bit complicated. Yeah, here it will benefit a lot from having a deformation merging. And do you get, yes, you can see that from a single, with filtering, you should be able to get out the strings, which is a pretty impressive fit. That will be hard to mimic with photogrammetry. So here, this is reality scan. This is just to get a glimpse. For example, the racket, we didn't have a lot of images, but let's see. So as you can see, 4 images, nothing in it, very bad. Let's just do a very quick alignment to see. And here we go. This is our reconstructed model. So you see, you may have some stuff around, but it's pretty hard to get something decent, right? Now let's make it totally with maybe the car. That would be a good example. So not the guitar, the car. Like all the images, I drop them. Let's align images. And here is the result. So the 3D mesh, there is a base point cloud under. Very bad reconstruction, and you see how it struggles to recreate the shiny surfaces. This is the really hard point for photogrammetric workflow. So this is really a great time for me to say that all of these techniques, it's super key to understand them, especially in the AI era, to then be able to build, like I do, solution around them, but also to have this critical thinking that makes you the expert that know when to use a technique over the other ones, because it will yield better results. So this is, of course, where I put most of my time trying to educate there and give the tools. So not only theory, but especially how to go from learning to building. The first stage is the 3D data science with Python book. But of course, if you really want to master everything, check out the new course on learngeodata.eu. It's fantastic. And there are a lot of people from various companies that will help you get better over time. All right, that's a wrap for me. I hope you got a ton of value. Remember, maybe subscribe to the channel if you want to get the notification about the new labeling strategy that is coming right away. In the meantime, don't hesitate to drop in the comment ideas that you would like us to work on together, or just join the community at learngeodata.eu to build your skills and future around spatial AI and 3D. See you very soon. Bye-bye.